So example 8.3.1, so confidence interval for the population mean using technology. So the data in table 8.3.3 are the life expectancies for a sample of men from each of the 53 European countries in 2011. And we're asked to find a 99% confidence interval for the mean life expectancy of all men in Europe in 2011. So this mean life expectancy of all men in Europe in 2011, in our symbols that will be mu, and we're asked to compute a confidence interval, so we're going to follow the acronym PANIC to get all of our steps there. So this one is a little bit different than other ones in the sense that each one of these numbers came from a sample itself. So to make sure we had representation across all the countries, so kind of like a stratified sample, they took a sample from each of the 53 and computed a mean life expectancy from just those samples. So this is actually a bunch of sample means instead of individuals within the data set to begin with. But we want to use that data now to try to help predict the mean life expectancy for all men in Europe back in 2011. And then again, we could look at sample data today to see if that has changed since then. All right, so the first step here in PANIC, the P stands for population parameter. So in this case, we're dealing with quantitative data. And so we are going to look at the mean life expectancy for mu. That's going to be for all European men in 2011. And in this case, this is going to be the mean life expectancy from these, 53 randomly selected countries of European men in 2011. Again, every inferential procedure has its assumptions that need to be checked, and again, those assumptions will be on your cheat sheet. So the first one is that we have a random sample of size n. Again, this one is a little bit weirder because it's actually like a stratified sample, but again, we're going to consider it random enough. So again, a random sample of 53 life expectancies of European men was taken. The data is actually based on a sample of life expectancies from every single country so that they're all represented in this number. But again, we're just going to still consider it random enough. The second condition is that we either need the population to be normally distributed, or we need the sample size to be at least 30, and we need to make sure that there are no outliers in the data set. In this case, we are given data, so we don't see the word normal anywhere in the paragraph, but we do in this case have a sample. In this case, n here is at least 30 because we have 53 numbers in our data set here. But we are going to run through the graph checks just to kind of refresh our memory on how we would do that. And also we still need to check that there's no outliers in the data set with a modified box plot. All right, so if we were to look at the histogram for life expectancies that of the numbers that we were given here, this is not very bell-shaped. It's kind of skewed. And in this case, we've got a longer tail off to the left, so left skewed. But again, this is an or statement, so it doesn't look like maybe the population might not be normally distributed, but we do have a sample size of at least 30. So let's check the other couple graphs we have here. So this is one of the important ones. So the modified box plot is the one that we use to make sure there's no outliers, and as we look to the extreme left and right, there are no dots on the modified box plot. So there are no outliers, which is a good thing, because that is one of our conditions that we need to check when we're given data. And if we look at the normal probability plot here, it doesn't look very linear. We've got this kind of big hump here in the up here in this part of the graph. So in here we're going to say it's not all that linear. So in this case, the population does not appear to be normally distributed, but that's okay because the or part of that statement is we need a sample size of at least 30. And again, we've got 56 is greater than or equal to 30, so that checks out. And the modified box plot shows no outliers, which is the other piece that we need there. All right, so if those conditions are met, we can still use this t-interval procedure. so our step 4, so panic, the fourth letter is I, so we're going to get our interval estimate, and along with that we're going to look at our point estimate. So again, if we go into the stat menu and we're going to type that data into L1, so again you should pause the video here because you should actually make sure that your input and output screens look like the ones that are shown here. So if we go into the stat menu, so if we do stat 1 and enter the original data set, those 56 data points into list 1, and then we're going to go into stat and over to the test menu to choose t-interval. We have data, so we're going to highlight data, and again if we put this data in L1, we're going to tell the calculator what list we put it in. So you don't have to put the data in L1. You could put it in L2 or some other list, but then you would just need to tell it what list you put things in. Frequency here, the default is 1, and we never changed that in this class, so that should still be set to 1. And in this case, we wanted a 99% confidence interval, so our confidence level is 0.99, and then we'd hit calculate. And again, on the output screen for t-interval, the first thing that we see here is our interval estimate for mu. So that interval runs from 71.632 to 75.84. And the next thing we see is the value of x bar, which is our point estimate for mu. And that we see is about 73.736 if we were to round that. In this case, this is quantitative data, so everything would have units with it, which in this case would be measured in years. Now, in StatCrunch, since it is a pretty big data set, we could go into Stat and t-tests and then choose one sample in with data. Again, that data is in Blackboard that you could upload to StatCrunch. Again, we would select that column, and next to confidence interval for mu, at the level we would put 0.99. And then on the output screen, we've got a column that says sample mean, so that's our value of x bar, and then our confidence interval endpoints are these last two numbers called the lower limit and upper limit. So no matter which technology we use, we're going to get the following. So for our point estimate, the value of x bar, if we round that off, is about 73.736 years. And the confidence interval for mu runs from 71.632 years to 75.840 years. So finally, the last letter in panic is C, and so we're going to write a conclusion in context with this. And so again, that interval before, we're 99% confident that mu is in that interval, and so we're just going to write in here in context what we defined mu to be at the start of the problem. So we are 99% confident that the mean life expectancy of all European men in 2011 was between 71.6 years and 75.8 years. And again, just like in the last section, sometimes these intervals, when we see these sort of things in newspaper articles and journal articles, are reported in a different way. So instead of the interval, they give the estimate and the margin of error. So in this case, we could say that we estimate that the mean life expectancy of all European men in 2011 is about 73.7 years. So that was our value of x bar, with a margin of error of about 2.1 years. So again, where did that 2.1 come from? Okay, so again, our central point here at 73.7, and the endpoints of our interval, this needs to be, the upper endpoint was 75.8. So if we take 75.8 minus 73.7, we get 2.1. And this lower endpoint needs to be 71.6. And so again, if we take 73.7 minus 71.6, we also get 2.1. Okay, so in this case, the interval estimate, we're giving it in this form of x bar, give or take the margin of error. So in this case, that would be 73.7 years, give or take 2.1 years.